In this video, we're going to focus on drawing the enol tautomer from a ketone. And we're also going to go over the mechanism under acidic and basic conditions, converting a ketone into its enol version. So let's begin. Let's say if we have acetone. How can we draw the enol tautomer of this ketone? Now we know that these two can interconvert, but the ketone form is much more stable. To draw the enol tautomer, rewrite the ketone as an alcohol, and then add a double bond, either on the left side or on the right side. In this case, it doesn't matter which side you put it on. And that's how you can draw the enol tautomer from a ketone. So now let's work on some examples. Let's say if we have a diketone, if we have two carbonyl groups. Now, where would you put the double bond? If you put it here, it's the same as putting it here, due to symmetry. As you can see, we have a alignment of symmetry right in the middle. If you place a double bond here, it's the same as placing it here. So let's focus on the right side. Should we place it to the left of the ketone on the right side or towards the right? What would you say? Well, let's draw both examples and let's see what we have. So we're going to replace this ketone with an OH group. Now let's put an OH group on the other one too. So for the one on the top, we're going to put the double bond on the right side of the OH group. And for the one on the bottom, we're going to put it on the left side. Now, which enol is more stable? Is it this one or this one? Since we have two possibilities. What would you say? Which one is more stable? Double bonds that are conjugated are more stable than isolated double bonds. These two double bonds are isolated from each other. They're very far apart. In the conjugated system, double bonds and single bonds alternate. You'll have a double bond, then a single, and then another double bond. And so it's stabilized by resonance. These two double bonds are conjugated with respect to each other. So therefore, this is the enol tautomer that we should draw. It's more stable than the other one. Nevertheless, this ketone form is more stable than the enol form. So the equilibrium is directed towards the reactants. Notice that we have a bigger arrow towards the left. Now for the first reaction, more than 99% is in the form of the ketone, and less than 0.1% is in the form of the enol isomer. Now for this particular example, it's much more stable. There's two reasons. But first, let me give you the relative percentages. About 85% is in the ketone form, and about 15% is in the enol form. Now, even though the ketone form is still much more significant, when you compare these two enols, 15% is far greater than 0.1%. 15% is about 150 times greater than 0.1%. So in terms of relative stability, this means that this enol is far more stable than this enol, even though both enols are less stable than the ketone forms. Now let's talk about the stability of this one. We mentioned one thing, which was the conjugation of the double bonds. So that's one factor that contributes to the stability. But there's also another factor, an intermolecular hydrogen bond, or rather, an intramolecular hydrogen bond. The hydrogen bond is between the oxygen atom and the hydrogen atom. It's not this bond here. The hydrogen bond is between a hydrogen and an oxygen that's not covalently bonded, which are these two. These two are covalently bonded. So this is the H bond. So that's why this particular enol is much more stable than the other one. It's due to conjugation, and it's stabilized by an intramolecular hydrogen bond. Let's try some more examples. Draw the enol tautomer for this compound, cyclopentanol. So for this one, we can put the double bond on any side. We have no other functional group that we have to worry about, so it really doesn't matter. As long as we convert the carbonyl group into an OH group and put a double bond right next to it, that's all we need to do. So what about this example? Let's say if we have a 6-membered ring with a carbonyl group and also 2 double bonds. How would you draw the enol version? So like before, the first thing you want to do is convert the carbonyl group into an OH group, and then decide whether you should put the double bond on the left side or on the right side. If we put it on the left, notice that we have the formation of an allene. Allenes are not stable, but if we put it on the right, notice that we have phenol, which is aromatic. Because of the aromaticity of the ring and the fact that it's conjugated, this particular enol tautomer is more stable than its ketone isomer due to the fact that the ring is aromatic. So notice that this arrow is bigger this time. The equilibrium favors the enol tautomer instead of the keto tautomer, and that's one of the rare cases when you get the enol tautomer as the major product. Let's try one more example. Go ahead and draw the enol tautomer for this one. So just like before, we're going to replace the carbonyl group with an OH group. And then should we put the double bond on the right side or on the left side? If we put it on the right side, notice that it's isolated with the double bonds in the ring. But if we put it on the left side, notice that it's conjugated. So this particular enol is the one that we want to draw. Now let's go over the mechanism for the base-catalyzed keto to enol conversion. Let's use acetone as our example. Now we need to show the alpha hydrogen. The alpha hydrogen is the hydrogen attached to the carbon that's one carbon away from the carbonyl group. That hydrogen is relatively acidic. And for a ketone, the pKa of that hydrogen is roughly around 20. So let's add hydroxide. We're going to use hydroxide to take off the alpha hydrogen. And when that bond breaks, these electrons will return to the carbon atom. Carbon is more electronegative than hydrogen. As a result, anytime you break a carbon-hydrogen bond, the electrons in that bond is pulled towards the carbon atom. So this is going to give us one of the resonance contributors of the enolate ion, which looks like this. To draw the resonance form, the carbon can take its lone pair, form a double bond, and break the pi bond of the carbonyl group. So we're going to have something that looks like this. This oxygen had 2 lone pairs, now it has 3. Notice that hydroxide grabbed a hydrogen, and now it's in the form of water. Under basic conditions, water is going to behave as the acid, hydroxide behaves as the base. And so now the oxygen with the negative charge is reactive enough to remove the hydrogen from water, regenerating the hydroxide base catalyst. And so now we have the enol tautomer. And so that's the mechanism for the base-catalyzed enol keto tautomerization reaction. Now let's go over the acid-catalyzed mechanism. Let's start with acetone once more. So this time, under acidic conditions, the acid is H3O+. The base is water. So the first thing that happens is we're going to have protonation under acidic conditions. Under basic conditions, the first step is deprotonation. By the way, this process is reversible. So now we have an activated ketone, which looks like this. And now the hydrogen is even more acidic due to the fact that the ketone has a positive charge, such that water is strong enough to deprotonate the hydrogen. So water is going to act as a weak base. It's going to grab the alpha hydrogen. The carbon-hydrogen bond is going to break, forming a double bond, causing the pi bond to break. And in that single step, the protonated carbonyl group will turn into a hydroxyl group. It had one lone pair, now it has two lone pairs. And we have a double bond here. And the fact that water grabbed the hydrogen means that it turned back into H3O+. So notice that the H3O+ ion was not consumed in the reaction. So it's a catalyst. It speeds up the reaction. And because it's an acid, it makes it an acid catalyst. So that is it for this video. Thanks for watching.